Hi, this presentation has two sections. The first section details Euler's proof of Girard's theorem that every prime of the form for n+1 is a sum of two squares. It's a proof that makes use of the infinite descent method plus the contradiction method and some elementary algebra properties. In the second and shorter section, we describe Euler's previous attempt to tackle the topic, where the Swiss mathematician proves that a prime of the form for n+3 cannot divide a sum of two squares if the squares are relatively prime. In 1658, Pierre de Fermat wrote a letter to Colonel Digby, a founding member of the Royal Society, affirming that every prime of the form for n+1 is of the form x squared plus y squared. That 3 and every prime of the form 6n plus 1 is of the form x squared plus 3 times y squared. That every prime of the forms 8n plus 1 and 8n plus 3 is of the form x squared plus 2 times y squared. That every prime is the sum of at most 3 triangular numbers, 4 squares, 5 pentagonal numbers, and so on. In 1747, Leonhard Euler wrote a letter to Christian Goldbach announcing that he had succeeded in proving Fermat's first statement, that every prime of the form for n+1 is of the form x squared plus y squared. This presentation will reproduce Euler's proof, which makes use of the infinite descent method developed by Fermat. His proof is divided into 5 parts. The product of two numbers, each of which is a sum of two squares, is itself a sum of two squares. In this statement, Euler demonstrates what is now known as Brahmagupta's identity. The process begins by expanding the product of two sums of squares and then rearranging the terms. We then add and subtract the product of two a, p, b, q, allowing us to regroup the terms into two perfect square trinomials. These trinomials can then be factored, resulting in a new sum of two squares. It's important to note that the first square includes a plus sign, while the second contains a minus sign. By reordering the 2 times a, p, v, q terms, we obtain another set of perfect square trinomials. Factoring these trinomials once again gives us an alternate sum of two squares. In conclusion, the product of a pair of sum of two squares is a sum of two squares, and this can be achieved in two distinct ways. If a number which is a sum of two squares is divisible by a prime which is a sum of two squares, then the quotient is a sum of two squares too. In this statement, Euler builds upon the identity derived in part 1. Due to the presence of both the plus and minus signs, there are two possible representations as a sum of two squares. Euler recognized that p squared plus q squared divides one of these representations, and consequently it divides the product of both as well. By expanding the terms of the product, we obtain a difference of two squares. Next, we add and subtract a squared times p squared and then regroup, leading to the expression a times the sum of p squared and q squared minus p times the sum of a squared plus p squared. Since both of these terms are divisible by p squared plus q squared, it follows that the initial product at the left of the equal sign is also divisible by p squared plus q squared. Given that p squared plus q squared divide the terms at the left of the equal sign twice, and that also divides the second square at the right side, it must also divide the first square. Therefore, we can divide all the terms by p squared plus q squared, resulting in a quotient that is itself a sum of two squares. If a number is written as a sum of two squares and is divisible by a number that is not a sum of two squares, then the quotient has a factor that is not a sum of two squares. Consider the sum of two squares, a squared plus b squared, with prime factors x sub 1, x sub 2, etc., and y. We assume that all x sub k factors are sum of two squares, while y is not, that it is a prime of the form for n plus 3. As demonstrated in part 2, if a prime factor of a sum of two squares is itself a sum of two squares, then the quotient is also a sum of two squares. Thus, we can successively divide a squared plus b squared by each x sub k, which is equal to p sub k squared plus q sub k squared, obtaining a smaller sum of two squares at each step. After dividing a squared plus b squared by all x sub k, we would be left with y, which would imply that it is a sum of two squares. However, since y is not a sum of two squares, this contradiction indicates that at least one of those x sub k factors cannot be a sum of two squares. We can illustrate that with an example. 72 squared plus 69 squared is divisible by 5, 13, and 17, all of them sum of two squares. By successively dividing 72 squared plus 69 squared by these factors, we eventually end up with 3 squared, which is the product of 3 times 3, where 3 is a prime of the form 4n plus 3. This example highlights that for a number to be a factor of a sum of two squares, any prime factors of the form 4n plus 3 must have even exponents. If they do not, the sum cannot remain as a sum of two squares. If a and b are relatively prime, then every factor of a squared plus b squared is a sum of two squares. To understand why, consider that if a squared plus b squared is a prime number, then a and b must be relatively prime. Otherwise, a common factor would divide that prime. That is a contradiction. It's impossible. Hence, we're dealing with a case where a squared plus b squared is composite, which has two or more factors, one of which is x. We compute the residues of a and b modulo x, giving residues c and d respectively. We can express a as m times x plus c and b as n times x plus d, where n and n are the largest quotient, and c and d are the smallest residues in absolute value. Next, we substitute these linear forms into a squared plus b squared and group the terms that are divisible by x. Since x divides that term and a squared plus b squared, then it must also divide c squared plus d squared. Thus, c squared plus d squared can be expressed as x times other factor. The greatest common divisor of c, d, and x is 1. Otherwise, the common factor will also divide a and b, and so they wouldn't be relatively prime. If there were a greatest common divisor c and d bigger than 1, say alpha bigger than 1, and after dividing c and d and y by alpha, that yields other sum of two squares, say e squared plus f squared, where e and f are relatively prime, just as a squared plus b squared was initially. If x were not a sum of two squares, then, as shown in part 3, a factor of w, say z, would also not be a sum of two squares. This would imply an infinite descent, starting with a sum of two squares, a squared plus b squared, where a and b are relatively prime. Then, if there were a factor x, not a sum of two squares, then there would be a smaller sum of two squares, e squared plus f squared, where e and f are relatively prime, and there's a factor z that is not a sum of two squares. That is, we got an infinite descent. Thereby, this deduction implies that every factor of a squared plus b squared is a sum of two squares when a and b are relatively prime. Every prime of the form 4n plus 1 is a sum of two squares. Fermat's fiddle theorem states that p divides a raised to p minus 1 minus 1 when a and p are relatively prime. As here we're dealing with primes of the form 4n plus 1, then we got that p divides a raised to 4 times n minus 1. That means that p divides each of these brackets. Let's illustrate this. Consider prime 13, which is of the form 4 times 3 plus 1. We can see that 13 indeed divides the differences too. And so p must also divide the difference of them. Then, for all values of a relatively prime to p, we got that p divides a raised to 4 times n minus a minus 1 raised to 4 times n, which can be factored as the product of a raised to 2 times n minus a minus 1 raised to 2 times n times a raised to 2 times n plus a minus 1 raised to 2 times n. The second bracket is a sum of two squares, and as the greatest common divisor of a and a minus 1 is 1, then, as shown in part 4, p must also be a sum of two squares. Thus, it remains to prove that p does not divide a raised to 2 times n minus a minus 1 raised to 2 times n. if p divides all the differences, then p divides all the differences of them, and also all the differences of the differences, and then all the differences of the differences of the differences, and so on. Let's illustrate this with a few examples. So p should divide the k differences as well, but they are all equal to k factorial. As here we're dealing with k equal 2 times n, then p, which is of the form for n plus 1, should divide 2 times n factorial, and that's impossible. So p can only divide a raised to 2 times n plus a minus 1 raised to 2 times n. To recap Euler's proof, start by affirming that the product of two sum of two squares is itself a sum of two squares, and that if a sum of two squares is divisible by a prime, which is a sum of two squares, then the quotient is a sum of two squares. Third, prove that if a sum of two squares, a squared plus b squared, is divisible by a number that is not a sum of two squares, then the quotient has a factor, y, that is not a sum of two squares. Because should we divide a squared plus b squared by all its factors that are sum of two squares, we would find that y is a sum of two squares, although it isn't. So at least one of those other factors of a squared plus b squared must not be a sum of two squares. Fourth, show that when starting with a sum of two squares, a squared plus b squared, where a and b are relatively prime, then if a factor x is not a sum of two squares, there would be a smaller sum of two squares, e squared plus f squared, where e and f are relatively prime, and there's a factor z that is not a sum of two squares, and so we enter in an infinite descent. Thus, every factor of a squared plus b squared is a sum of two squares when a and b are relatively prime. Finally, Euler demonstrated that every prime of the form for n plus 1 is a sum of two squares by noticing that Fermat's theorem determines that p divides a raised to 4 times n minus 1 for all a co-prime to p. So it also divides the difference of any a raised to 4 times n minus a minus 1 raised to 4 times n. If p divides a raised to 2 times n plus a minus 1 raised to 2 times n, it must be a sum of two squares as shown in the previous paragraph. If p divides a raised to 2 times n minus a minus 1 raised to 2 times n, then it divides all a sub I raised to 2 times n minus a sub I minus 1 raised to 2 times n, and also divides the differences of them, and the differences of the differences, and so on. But the 2 times n differences are equal to 2 times n factorial. Thus, p cannot divide it, arriving to a contradiction. So it can only divide a raised to 2 times n plus a minus 1 raised to 2 times n, and so proving that it is a sum of two squares. As noted in the first section, in 1747, Leonhard Euler wrote a letter to Christian Goldbach announcing that he had successfully proved that every prime of the form for n plus 1 can be expressed as x squared plus y squared. 5 years earlier, in 1742, Euler informed Goldbach that he had demonstrated that a prime of a form for n plus 3 cannot divide a squared plus b squared if a and b are relatively prime to p. Euler's proof begins by leveraging Fermat's theorem, showing that p divides a raised to 8 times n plus 4 minus b raised to 8 times n plus 4. As when adding and subtracting 1, we can factor these brackets, revealing a raised to p minus 1 minus 1 in the first term, and b raised to p minus 1 minus 1 in the second term. Applying Fermat's theorem, we know that p divides them, as each of them are relatively prime to p. Thus, p divides a raised to 8 times n plus 4 minus b raised to 8 times n plus 4, as one factor yields a raised to 4 times n plus 2 minus b raised to 4 times n plus 2, and by adding and subtracting 1, we know that p divides each difference. Furthermore, p cannot divide a raised to 4 times n plus 2 plus b raised to 4 times n plus 2. and one factor, here you see that the sum of the two squares, a squared plus b squared, appears. P cannot divide a raised to 4 times n plus 2 plus b raised to 4 times n plus 2, because if we add and subtract 1, then, because of Fermat's little theorem, it would divide a raised to p minus 1 minus 1, but not divide b raised to p minus 1 plus 1. Hence, p cannot divide a raised to 4 times n plus 2 plus b raised to 4 times n plus 2. Consequently, a prime of a form 4n plus 3 cannot divide a squared plus b squared if a and b are relatively prime to p. That's all, folks. Thanks for watching. If you enjoyed this content, don't forget to give it a thumbs up, leave a comment with your thoughts or questions, and share it with anyone who might find it valuable. If you haven't already, consider subscribing to my channel for more elementary number theory content. Stay tuned for future videos by hitting that notification bell so you never miss out. Your support means a lot.